Hi, in this video I'm gonna show how to use our software for GPS spoofing resilience testing. I will perform coherent and non-coherent attack scenarios. Let's start with the required hardware and connection diagram. Okay, what we have here. To use the application, you need a software-defined radio from Ethos Research with an embedded GPS disciplined oscillator. In my case, I use the USRP B200 board. Also, you need a GNSS receiver from uBlocks. It's needed to get live GPS signal parameters, and it's used as a reference in our tests. Here you see an electromagnetic shield to reduce parasitic radiated power. It's not included in the standard package of the board, and we make it ourselves. It really helps to avoid self-spoofing of the reference receiver and the GPS DO. Okay, during the test I am going to spoof this GNSS module. It's exactly the same as the reference one. And it will be the test over the cable. Here you see some RF accessories. This is the cable from the GNSS antenna from my windowsill. Then we see two power dividers. It's used to share one GNSS antenna between three receivers. 1, 2, 3. This is a directional coupler to mix the spoofer signal with the original signals. And in addition, we use two 10 dB attenuators to reduce the output power of the spoofer. In total, we have about 44 dB of signal attenuation along this path. This coupler has at least 20 dB of directivity. This means that the spoofer signal over this path is attenuated by 20 dB. Additionally, here we have about 30 dB of isolation between the channel of the divider. In total, this gives us at least 50 dB of spoofer signal attenuation at the input port of the reference receiver and GPS DO. Okay, I guess it's clear, and let's switch to software. Okay, we are using uCenter from uBlocks to configure the target receiver. Here you see the visible satellites. Beginning with E is Galileo, with G is GPS and GLONASS. I'm not going to show how to attack a multi-constellation receiver. That's why I'm going to disable the tracking of Galileo and GLONASS now. Let's open Messages window, go to UBX, then Config and GNSS, and let's disable Galileo and GLONASS. Click Send. Okay, now we see only GPS satellites, and let's open the coordinates deviation map. It will be used as an indicator of a successful attack. Here it is. Okay, it's done. Let's switch to our simulator. Usually solutions for generating GNSS signals are complicated and require deep knowledge. In contrast, we have made a simple tool for vulnerability testing. It's perfect for cybersecurity specialists without any GNSS background. Let's see how true it is. Here you see the data from the reference receiver, timing, coordinates, and visible satellites. And there is only one setting here. You just need to select the connection port. Next, time configuration. We can simulate current time and past time. Why not the future? We use the real almanac and ephemeris files from the NASA archive, and they do not exist for the future time. The current ephemeris data is only valid for the next 2 hours. Let's download the files, and you must be registered and enter your login and password here. Okay, it's done. This may be the most important setting. It's a spoofing type. We start from asynchronous or non-coherent attack scenario. Next one, hardware setup. Here we can configure the connection to the device under test over there and over the cable. Otherwise it's also called radiated or conducted testing. In our case, we only need to enter the total attenuation of the spoofer signal. It's about 44 dB, as you remember. And let cable length be 1 meter. Here you see the available power at the receiver input port. That's good. The power level of the original signals at a GNSS receiver input port is usually in range of -130 to -100 dBm. It really depends on antenna preamplifier gain, cable length, weather, and so on. In my case, it's about -100 dBm. Now let's set up the initial simulated coordinates. This can be done manually, or we can specify an offset from the spoofer position, offset by the ground, and height. Let's make it 500 meters. That's all. We start from the minor power level. Okay, let's get started. Great, the simulation started. However, we do not see any effect here. Let's try to increase the power of fake signals. We're generating quite a lot of power, but the receiver still has not been spoofed. What's going on? A non-coherent signal is not synchronized with real one and is not perceived by the receiver. For a successful attack, we need to block the reception of real signals. This can be done by increasing the power of fake signals. Let's do it. Okay, let's increase the power. More and more. Finally, the receiver has lost tracking of live GPS signals and switched to fake ones. Take a look over here. The coordinates have shifted by 500 meters, exactly as we configured in the simulator settings. Now we don't need that huge power. We control the receiver now and can, for example, change the power of some satellites. For example, for number 22. And 25. Obviously it works. Let's move to the real receiver position. Going east. And move it up a little more. Okay, it's done. Let's disable the spoofer. You can see here that the receiver has lost fake signal tracking and is trying to find a new one. It's going to take some time. Let's wait. Finally it works. As you have seen, with the non-coherent attack, we needed to generate a huge power to block the original signals. The receiver under test malfunctioned at the beginning and at the end of the attack. Satellites were blinking, there was a loss of tracking. Let's now launch a coherent scenario. Let's go to the time settings and select synchronous or coherent attack. Let's clear offset. And let's get started. The synchronous signal generation does not start immediately. The application waits for GPS frame beginning, so we have to wait. Great, it launched. As you can see here, the signal to noise ratio for all satellites has jumped. The receiver did not lose tracking and instantly switched to fake signals. Let's draw a square, for example. First, we go west. Great, now let's go north. Now east. And finally, let's go south. Okay, now we are on the original point. Let's see what happens if we disable the spoofer. Did you see that? The receiver switched to the original signals without losing signal tracking. That's really amazing. Coherent spoofing has a number of key advantages. Switching to fake signals is instantaneous, no huge power required, no loss of signal tracking. Subscribe to our channel. Next time I will demonstrate 2 techniques to spoof a multi-constellation receiver.